Welcome to this FP2 video on the Taylor series. So the Taylor series is, for lack of a better word, the general version of the Maclaurin series, or the Maclaurin series comes from the Taylor series. You could say that as well. Now, in previous couple of videos, we looked at the Maclaurin series expansions. To write a function of x as an infinite series in its ascending powers of x. However, we had to make sure that x was equal to 0, and then values of x that were very close to 0, a few terms of the series would give a good approximation. But if we had values of x that stayed within the limits, the interval of validity, sorry about that, but if they were larger values of x but still acceptable values, you would need more terms of the series to get an accurate answer. Okay, so to overcome these kinds of problems, a series expansion focusing on x equals a can be derived, and this expansion is called the Taylor series. Okay, so you can think of it as a more general form of the Maclaurin series. And at this point, feel free to skip on to the first example. Otherwise, I'll just give a little bit more. So we're considering the functions where f of x plus a is equal to another function g of x. These are equivalent. Okay, then f r, so it's been differentiated a few times, is equal to g r of x, where r equals 1, 2, 3 and so on, and in this a cannot be equal to 0. So that means that this is also the case. Okay, so if x is equal to 0, then the differentials of when we've got the a value is equal to this. Now this is like the Maclaurin series expansion, so let's put that down. So g of x, and there we have it. We didn't need to see me write that down. Now this becomes, when I put f of x plus a, becomes f of a plus f dash of a times x and so on. Okay, and these two are obviously the same as these two are the same. Now, I call this one a. Now, if we replace x with, instead of being 0, with an x minus a, we get another useful form. So if x is x minus a, and I substitute it into here, I'd get x minus a plus a, which is just f of x. Okay, and then I get f of a plus f dash of a. Now instead of times by x, we times them by x minus a, plus f double dash of a over 2 factorial times x minus a squared. And you can hopefully now see the pattern. All the way up to a general one and call this B. So now we have two expansions A and B, and these expansions are known as the Taylor series expansions of f of x at or about the point x equals A. Now bear in mind the Taylor series expansion is valid only if f n of A, so this f, so my derivative of f of x with A inside as replacing x, exists and is finite for all values of n and for all values of x for which the infinite series converges. Okay, so the series, it always has to converge to a particular value. Okay, if it doesn't converge, then this series expansion is not going to work. Anyway, there is plenty of other videos on YouTube explaining more of the Taylor series. If you do wish to find out more, then please just do a little bit of a search and sit down and enjoy a few of those videos. But for now, we want to be able to do these questions leading up to our exam, okay, because you've got exams to do the end of this year, of this academic year, and you need to know to be able to do these. Not all of this is going to be massively interesting to everyone. Okay, some of you just want to be able to do it. So let's have a little look at a couple of examples of how we go about this. So this is a past paper question. The Taylor series expansion is the part B, but let's look at part A first of all. So we've got y equals x e to the power x. So let's work out dy by dx. So it's going to be this times this differentiated, x e to the x, plus this times this differentiated, e to the x. And that will be e to the x if I substitute it out, and x plus 1 inside my bracket. Now let's differentiate a second time. Now looking at this first one, okay, this is going to be the same as this, so it's going to repeat and give me this. So x e to the x plus e to the x. That's differentiating that, and then I've got to differentiate this, which is going to be e to the x, so plus e to the x, which is going to give me x e to the x plus 2e to the x, and then e to the x, factorizing that out, we've got x plus 2. So I think I can see a pattern appearing here. We'll do it a third time just to be sure. We do know what we've got to show, so you know we do need to do it enough times to show that. Now differentiating this is just going to be this, so x e to the x plus e to the x, and then differentiating 2e to the x is going to be 2e to the x. So that's going to be x e to the x plus 3e to the x, which is e to the x outside, x plus 3. Now we've shown enough to get our pattern. If we didn't know this, we could have probably done it after 2, maybe gone to the third one just to be sure. You should always go to 3 just to be sure. Okay, so each differentiation struggled with the spelling then, adds another e to the x. Okay, therefore dny by dx to the power n is equal to e to the x plus n. That's required. Okay, so that is part A complete. Now let's move on to part B. Okay, part B is find the Taylor series expansion of x e to the x in ascending powers of x plus 1 up to including the term x plus 1 to the power 4. So first let's let f of x equals x e to the x. I could have kept it in terms of y up here, but f of x is easier to deal with my notation. Okay, and a will be minus 1 because we've got the x plus 1. Now here we're going to use the Taylor series expansion, the B one. Okay, so this says that f of x is equal to now f of minus 1. And that is, now I'm just going to get rid of part A. That's better, got a bit more room now. So I'm just substituting in to that part, that expansion B. And the last one is there. And obviously this would continue on, but we don't require it to go any further. So let's substitute these in. So I'll just work out each one first of all on the side. So minus 1 going into my f of x is going to be minus 1 e to the minus 1. Minus e to the minus 1. And then f dash of x, when I substitute minus 1 in, it's going to be 1 minus 1, so it's going to be 0 e to the minus 1. Sorry, that isn't an x there. That is a minus 1. Now, when I put in 2, remember we've got x plus 2 in this bracket. So 2 minus 1 is 1. E to the power minus 1. 3, the third one will be 3 minus 1, which is 2 e to the minus 1. And the fourth one is going to be 3 e to the minus 1. So these now I need to substitute in to my expansion. Okay, so f of x is obviously x e to the power x, so x e to the power x, and that is minus e to the minus 1 plus, oh, that's going to be 0, plus minus, no, it's just e to the minus 1 x plus 1 squared over 2 plus 2e to the minus 1 x plus 1 cubed over 6 plus, and then the fourth one is 3e to the minus 1 x plus 1 to the power 4 over 4 factorial, which would be 24. And now we've just got to simplify it. So minus e to the minus 1 plus e to the minus 1 over 2 x plus 1 squared plus e to the minus 1 over 3 x plus 1 cubed plus e to the minus 1 over 8 x plus 1 to the power 4. And I could alternatively factorize out the e to the minus 1. So I could just have then a half x plus 1 squared plus a third x plus 1 cubed plus an eighth x plus 1 to the power 4. Okay, and that now is the Taylor series expansion for x e to the x. Okay, my second example. So find the Taylor series expansion of sine x minus pi by 3 in ascending powers of x up to and including the term x to the power 4. So this one, ascending powers of x, it's not ascending powers of x plus 1 like in the last one. Okay, those ones we had to use the b expansion. This one, because they're ascending powers of x, we use the a expansion. Okay, but before I do that, we need to do our differentiating. So first, now let's let f of x equals sine x. Okay, therefore sine x minus pi by 3 is going to be equals to f of x minus pi by 3. Okay, so f of x equals to sine x. So this is now f of minus pi by 3 that we're substituting in is going to be, put an arrow there, sine of minus pi by 3, which is minus root 3 over 2. Now let's differentiate. Sine differentiates to cos x. So then f dash of minus pi by 3 is substituting that into cos. And that's going to give me a half. And then differentiate a second time. Cos differentiates to minus sine. So f double dash of minus pi by 3 is going to be minus sine minus pi by 3, which is going to be root 3 over 2. And then f triple dash. So sine differentiates to cos, so minus sine will differentiate to minus cos. And then substituting minus pi by 3 in, we get minus cos of minus pi by 3, and that gives me minus a half. And then when I differentiate a fourth time, minus cos, cos differentiates to minus sine, so minus cos will differentiate to sine x. And then substituting minus pi by 3 in, we get sine of minus pi by 3, and that is back round now, isn't it, to minus root 3 over 2. So that's my differentiations and my substitutions in for my f of x. Now let's go ahead and look at the expansion. So we're going to use, like I said, the Taylor series expansion A. Okay, so that is f of x plus a equals f of a plus f dash of a times x plus f double dash of a times x squared over 2 factorial and so on. And here it is just to remind you. So the f of x plus a is just my sine x minus pi by 3. And then I'm going to substitute each of these values in. So f of a is going to be minus root 3 over 2 plus a half x plus root 3 over 2 x squared over 2 factorial plus, now the third one is, oh sorry, it's going to be minus now. So we got minus a half x cubed over 3 factorial, or if I just write that down as 6 plus, and then the fourth one is, oh sorry, so it's minus root 3 over 2 x to the power 4 over 4 factorial, which is 24. Now just sorting these out, we got minus root 3 over 2 plus x over 2 plus root 3 over 4x squared minus x cubed over 12 minus root 3x to the power 4 over 48. And that is my Taylor series expansion of sine x minus pi by 3. So now I've shown you 2 examples, one where we use the A expansion, this one, and one where we use the B expansion, which was the first example. I suppose I could have done them the other way around, but anyway, they're done now. So that's now how you go ahead and decide which expansion to use. It all depends on the question. Okay, whether you're expanding something like this in powers of x, okay, and that means you use the A version. And if you're expanding in powers of like x plus 1 or x minus 1 or x plus 4 or whatever it might be, then you use the B expansion. Okay, so hopefully that makes sense to you and you found this video useful so far. If you have, hit that like button. If you are yet to subscribe to the channel, please consider hitting that subscribe button. Okay, it'll help you find me if you want to watch some more videos. If you're doing international A-level maths, it's very useful, but also other A-levels of maths, because the pure section is pretty much the same regardless of which exam board you are sitting. And if you're willing and able to help me out financially, hit that join button. Otherwise, let's look at a few questions. So I've got 4 questions for you here. They're all past paper questions ranging, well, all roughly 6 marks each. Okay. Yeah, pretty much. I mean, if it's just a Taylor series expansion like here, this is probably worth 4 marks. These 2. The ones with an additional part is worth 6 marks, and this one is just is worth 6 marks on its own. Okay, so giving you a rough idea of how many marks they're worth. So pause the video, have a go at these questions, and then jump back in to see the answers. Okay, hopefully you're ready to have a look at some of the solutions. Let's start with question 1. Okay, so part A, let's let f of x equals x cubed ln x, and a is going to be equal to 1. Okay, it's just the value that makes the bracket 0. Now let's differentiate. So f dash of x is going to be So differentiate this times this. So we've got 3x squared ln x plus, and then this times this differentiated. So x cubed times 1 over x is going to be x squared. So it's going to be, take x squared outside, 3 plus ln x. Sorry, that's not right, because it's 3 ln x. 3 ln x plus 1, isn't it? Like an idiot. Right, that's that one done. Right, f double dash of x. Now let's differentiate this one. So this differentiate is going to be 6x ln x. So 6x ln x. Now plus 3x squared times 1 over x will be 3x plus x squared differentiated is going to be 2x. So I've got 6x ln x plus 5x. And I could factorize out the x out, so I've got 6 ln x plus 5 in the brackets there. Right, let's differentiate a third time. So 6x differentiates to 6 ln x plus, and then 6x times 1 over x is 6 plus 5. So this is now 6 ln plus 11. Now differentiating this a fourth time, it's no longer the product rule. Ln x is going to be 1 over x, so 6 over x, and the 11 will disappear. Okay, so that is my differentiations. Now I need to substitute 1 in terms of x. Okay, so let's do f of 1. Well, it's going to be 1 cubed ln 1, which is going to be 0. Right, f dash of 1, that's going to be 1 squared 3 ln 1 plus 1. So 0 is 1, so this is going to be 1. And then f double dash of 1, that's going to be, so 1 times 6 times 0 plus 5. So this is going to be equal to 5. And then we want the third differential. So it's going to be 6, oh that's an ln x down there, plus 11. So it's just going to be 11. And then the fourth one is going to be 6 over 1, it's just going to be 6. So there I've got my first set of values. Now this is going to be the Taylor series expansion of the B one. Now just to remind you what that looks like, here it is. So my f of x was x cubed ln x. Now f of a, that's my f of 1, which is going to be just 0, plus then I've got 1 x minus 1, plus now 5 x minus 1 squared over 2, plus 11 x minus 1 cubed over 3 factorial, which is 6, plus 6 x minus 1 to the power 4 over 24. So that means that x cubed ln x is going to be x minus 1 plus 5 over 2 x minus 1 squared plus 11 over 6 x minus 1 cubed plus 1 over 4 x minus 1 to the power 4. And there we have part A complete. Now part B is relatively straightforward, just a substitution. Now let's look at it. So we want an approximation for ln 1.5. Okay, so ln 1.5, so x is 1.5. So 1.5 cubed, so if I do that in my calculator, I get 27 over 8 ln 1.5. And then this is going to be 1.5 minus 1 plus 5 over 2, 1.5 minus 1 squared, plus, and I won't keep on writing the 1.5 minus 1, because 1.5 minus 1 is just 0.5. So 0.5 cubed plus a quarter, 0.5 to the power 4, and so on. Okay, so that's going to give me, so this is an approximation, so I should use an approximation sign rather than an equals sign. So 0.5, and then I've got 0.5 squared times 5 over 2, and that's 5/8, so 0.625. Then I've got 0.5 cubed, which is an eighth, times 11 over 6, which is 11 over 48, which I'll keep as a fraction because the decimals are quite big there. So 0.5 to the power 4 is a 16th, times by a quarter is 1 over 64. Okay, so if I add that up, 1 over 64 plus 11 over 48 plus 0.625 plus 0.5, I get the fraction 263 over 192, and that's 27 over 8 ln 1.5. So now I need to divide by 27 over 8, so therefore ln 1.5 is going to be 8 over 27 times 263 over 192, so times in 8 over 27, I get 263 over 648. Now we need this to 4 decimal places, so 0.405, and then it's 86, so this is going to be 9. Okay, now if you do ln 1.5 in your calculator, you get the answer 0.4055, so it's just slightly off to the real value. Okay, obviously the more expansions we do in terms of this series, the larger we make this series, the more accurate our approximations would be. So that is the first question done. Let's look at question 2. Okay, find the Taylor series expansion of sine 2x about pi by 6 in ascending powers of x minus pi by 6 up to and including the term in x minus pi by 6 to the power 4. So this is going to be using the B expansion that we did in the last question. Okay, because we're going up in powers that look like this rather than just x's. So let's let f of x equal sine 2x and a equals pi by 6. And now let's go ahead and differentiate. So we need to go up to x to the power 4. So we need to differentiate 4 times. So sine differentiates cos. This is going to be 2 cos 2x, and then it's going to be minus 4 sine 2x. Sorry about that, we just there we are. And this is going to be sine differential cos, so this is going to be minus 8 cos 2x, and then we get back round to sine, this is going to be 16 sine 2x. Now we need to go ahead and substitute pi by 6 into my f. So f of x, so f of pi by 6 is going to be, so it's going to be 2 times pi by 6, so it's actually going to be pi by 3. Okay, so when I substitute that in, I'm going to get root 3 over 2, because it's like sine of 60 degrees, isn't it? F dash of x, oh sorry, it's not f dash of x, it's f dash of pi by 6. So substitute in pi by, well, it's really pi by 3, is that 2 pi by 6 in. So cos of that times by 2 is going to be 1. Okay, now sine of pi by 3 is going to be root 3 over 2 times by minus 4. So this will be minus 2 root 3. Now cos of pi by 3, now I'm saying pi by 3 because it is 2 times pi by 6, yeah? So cos of pi by 3 is a half times by minus 8 is going to give me minus 4. And then the fourth one, we've got root 3 over 2 times 16, so 8 root 3. Okay, and there we have our values. So now we need to use this expansion. So we've got sine 2x, and that's going to be the first one, root 3 over 2 plus 1 times x minus pi by 6. Now it's not 1, it's minus 2 root 3 pi by x minus pi by 6 squared over 2 factorial minus 4x minus pi by 6 cubed over 3 factorial plus 8 root 3 times x minus pi by 6 to the power 4 over 4 factorial. Now all I'm going to do now is just simplify this. So we've got root 3 over 2 plus x minus pi by 6 minus root 3 x minus pi by 6 squared minus 2/3 x minus pi by 6 cubed plus 1/3, sorry, it's not 1/3, it's root 3, isn't it? Root 3 over 3 x minus pi by 6 to the power 4. And that, ladies and gentlemen, is my Taylor series expansion of sine 2x about pi by 6 up to and including x minus pi by 6 to the power 4. Okay, and obviously you could keep on going if you needed to find the fifth one and so on. Okay, let's look at question 3. Okay, find the Taylor series or a series expansion of tan x minus alpha about 0, where alpha equals arctan 3/4 in ascending powers of x. So ascending powers of x means that we're looking at the expansion a, okay, which I just put up now. And we need to go up to the x squared term. So let's let f of x equals tan x minus alpha. So if I substitute x equals 0 in, so f of 0, then we've got tan of minus alpha. Now this is going to be the same as minus tan of alpha. Okay, you can just think of it in terms of the cast diagram if you wish. If this is alpha, then minus alpha will be here. So that's why cos minus alpha would equal cos alpha. Sine minus alpha would equal minus sine alpha. And tan minus alpha would equal minus tan alpha. Okay, it's a quick way you can kind of work out what's going to happen, whether it's going to be positive or negative. Anyway, so we've got tan of minus alpha equals minus tan alpha. Now from this up here, the arctan, we can say that tan of alpha is equal to 3/4. So minus tan of alpha will be minus 3/4. Okay, so that is my first one. Obviously the zero's in here because we're about 0. But in some of these questions, that's the only real way of doing that. Now let's differentiate first time. So tan will differentiate to sec squared, and it's x minus alpha, which if you differentiate the inside, it's just going to be 1, isn't it? So this is going to stay the same. Now substituting 0 in, we get sec squared of minus alpha. Sec is 1 over cos, and cos of minus alpha is just cos of alpha. So this is going to be sec squared alpha. Now we can use this up here to just, without working out what alpha is, tan is opposite over adjacent. So this hypotenuse is going to be 5. So cos alpha will be adjacent over hypotenuse, which is 4 over 5. So this will be 5 over 4 squared, or 25 over 16. Now we need to differentiate a second time. So this is sec x minus alpha all squared. So differentiating 2 comes down. So we got 2 sec x minus alpha. Differentiating sec x minus alpha will be sec tan. So this will be sec x minus alpha tan x minus alpha, or 2 sec squared x minus alpha tan x minus alpha. I can see why they don't want us to differentiate a third time, because it's starting to get more and more difficult. So now we substitute 0 in, and we get 2 sec squared minus alpha tan minus alpha. So I've already worked out what sec squared minus alpha is. So that's 2 times 25 over 16. And I've already worked out tan of minus alpha is, that's minus 3/4. So 25 times 3 times 2. So it's going to be 150. It's going to be minus 16 times 4 is 64. So 150 over 64, we'll just be able to take a 2 out. So it's 75 over 32 and it's negative. So now I'm going to make a little bit more room. And now let's substitute into my series. So we've got tan x minus alpha, and that's going to be equals to minus 3/4 plus 25 over 16 x minus 75 over 32 x squared over 2 factorial. So that's going to be minus 3/4 plus 25 over 16 x minus 75 over 64 x squared. Obviously the series does continue on, but that's as far as we need to go. Okay, and that is question 3 done. Hopefully you managed to get this out, and if you didn't, hopefully you managed to follow my workings. Now let's look at number 4. Right then, to show this, the first thing we need to do is to differentiate. So let's start with letting f of x equals ln x. Then f dash of x is going to be 1 over x. F double dash of x will be minus 1 over x squared. F triple dash of x is going to be positive. Bring the 2 to bring the minus 2. I'm sorry, I'm just doing it in my head. So it's going to be 2 over x cubed. And that's probably as far as I need to go, but I'll do the fourth one. This is minus 6 over x to the power 4, and then so on. So f of 2 is going to be ln 2. F dash of 2 is going to be 1 over 2. F double dash of 2 is going to be minus 1/4. F triple dash of 2 will be 2 over 8, which will be 1/4. F triple dash of 2 will be 6 over 16, which will be 3 over 8. Now we're going to use the series expansion b. So actually let's find the rth term, but because I don't want to use an r, I'll just change it to a k. Okay, so what would it be, the kth term? So this is going to change sign each time, isn't it? Positive, negative, positive, negative. So I'm going to have to times it by minus 1. Now, the second one is going to be negative, so I can't have it to the power k. So k minus 1 would make sense, because then the first one would be to the power 0, which is just 1. The second one would be to the power 1, which would be minus. The third one would be squared, which would be positive. The fourth one would be cubed, so it would be negative. So that's getting my sign changes done. Now let's work out the top values. So if I look backwards, this 6 is 3 factorial. The next one's going to be multiplied by 4, which will be 4 factorial. So the fifth one will be 4 factorial. The fourth one is 3 factorial. The third one is 2 factorial. So this is going to be k minus 1 factorial. And then it's going to be over x to the power k. So that's what we've got here, and then let's substitute not 1, sorry, not 0, 2 into this. So we've got minus 1 k minus 1 times k minus 1 factorial over 2 to the power k. So that now is my, general term of this sequence. So if I'm substituting it in to my f of x, so f of x, so this will be, my f of x of ln x is going to be ln 2 plus, and then I've got this general term which will give me all of these terms. Okay, but before I jump in like that, let's actually write it out. So we'll have a half x minus 2 plus, minus a quarter x minus 2 squared plus a quarter x minus 3 cubed minus, this should be in a minus here, minus 3/8 x minus 3 to the power 4, and so on. Now this would have been over, I've made a little bit of a mess up, so this, I've forgotten the 2 factorial. So this would have been over 4. The quarter would have been 3 factorial on the bottom, so it's going to be 4 times 6, 24. And this one would have been 1 over 96. And this one would have been over 960, which would cancel out. But let me just make a little bit of space, and let's add on my bottom one. So it's minus 1. We're going to use n minus 1, n minus 1 factorial over 2 to the power k. Now this is going to be times by x minus 2 to the power n over n factorial. Okay, so this bit and this bit then is multiplied onto this. This gives me this bit. Okay, now all of that, so this section is just a sum. Okay, so from r equals 1 to infinity. Now if I substitute 1 into this, I get minus 1 to the power 0, which is 1, over 2 times 1 factorial, so it's 2. And then I've got, that's going to be 0 factorial, which is just 1, and that's going to be x minus 2. So this is going to give me 1 over 2 x minus 2, where I've got 1 over 4. If I look at the second one, this one, I've got minus 1 to 2 minus 1, so that's going to be negative. It's negative. 2 minus 1 is 1 factorial, which is just 1. This is to the power 2, that's right. 2 squared is 4, times 2 is 8. So this term here is going to be, this is going to be 3 off, isn't it? So the first one was a half and we wanted a quarter. So let's write these down. A half and we wanted a quarter. When n equals 1. When n equals 2, we get an eighth, and we want 1 over 24. So it's times 3 times 2. And then when we substitute n equals 3 in, and you can put this down as you're working out on the side. Okay, so 3 minus 1, so that's going to be positive, which is what we want, positive. 3 minus 1 is going to be 2, so it's going to be 2. That cubed, that's going to be cubed. So we're going to have on the top 2 over, now 2 cubed is going to be 8, but they will cancel with this one, leaving me with 1/4 times 2, so we're going to get an eighth there, and we want 1 over 96. Okay, so we want to be times by 12. Let me just double check these values again. So we got a half, going in here, so that's, these values are wrong. Right, let's do these values from the start. So this is f dash of 1, so this is a half. Let me rub out this. Then we've got minus a quarter, divide by 2, so minus an eighth. Then we've got a quarter, divide by 6, so 1 over 24. Then we got minus 3 over 8, divide by 4 factorial, and that's minus 1 over 64. Okay, right, let's get rid of this. So let's look at white. So we substitute 1 in here, we get 0, 0 factorial, so that just stays as that to the power 1 over 2 times 1, so that bottom one is going to be a half. Oh yeah, I've got it. Now what do we want? We want a half. Now substitute 2 in, we get, that's going to be positive, that's going to be 1, that's going to be squared, yeah, and we get 2 to the power 2, which is 4 times by 2, which is 8. So that's right, and what do we want? Minus an eighth. Right, substituting 3 in, so that's going to be 3 minus 1 squared. Sorry, that was a minus there. So start again, right? Substitute 3 in. So that's going to be squared, so it's going to be positive. 2 factorials, it's going to be 2 on the top. And then we've got 2 cubed, which is 8. 8 times 3 factorial is 48, but we had 2 on the top. 2 over 48 is 1 over 24. And what do we want? We want 1 over 24. So substituting these n values into this is giving us this, as long as I've got this n factorial there. So this now is what should be in my sum. So I would perhaps have this working out on the side, but this now is going to be the sum of minus 1, n minus 1, n minus 1 factorial, x minus 2 to the power n, all over 2, that's to the power n, that's to the power n, n factorial. And now that does simplify to the answer that we want, doesn't it? So minus 1, n minus 1. Now, n minus 1 factorial over n factorial is just going to be n. No, it's just going to be 1 over n. Because this is n minus 1 times n minus 2, and this will be n times n minus 1 times n minus 2, so all subsequent terms will cancel. Okay, so you can say since this, then we've got x minus 2 to the power n over 2n times by n, and that is what's up there, isn't it? Ah, there we are. So that was a very painful question. Sorry about I perhaps should have rubbed some of this out and re-videoed it, but you got to see me working it out from scratch, making mistakes, and then double checking and finding the right answer in the end. Hopefully that was useful to you. If it was, don't forget to hit the like, subscribe if you're yet to, and please hit that join if you're willing and able to help me out financially. It does really help me make videos, or will hopefully in the future enable me to make more videos.